All right, so in this video, we're going to start talking about topic 3, which is called thermal physics. We are officially done with topic 2, which is mechanics, which we started way back in September. And so we are moving on to a completely different topic in IB physics. This topic is a more conceptual topic. It is less computational. There are calculations, of course, there's calculations in every unit, but there's also a lot of concept things that you just need to know. I will say that this unit is, this topic is much shorter than topic 2. We did, I think, like, 6 or 7 units in topic 2. We're only going to do 1 unit in topic 3. And so this is going to be like, 3.5 weeks, and then we will be done with topic 3. I will also add that generally speaking, people do really well with topic 3. I don't know if it's just, easier or if it's just more intuitive or just because it's not mechanics. But people tend to do really well on this topic. And maybe it's because some of the concepts you're familiar with from your past science classes. Okay, and so topic 3 is called thermal physics, and basically we're going to be looking at the concepts of heat, temperature, pressure. We'll be talking about ideal gas law later. We'll be talking about specific heat, latent heat, phase changes, and things of that nature. And so we're going to start off this unit by taking a look at a simulation. Of the atoms or molecules making up an object. And so I'm going to link the simulation so that you can load it. And then I want you to leave space in your notes to answer the following questions using the simulation. And so you're going to um, to write down these questions, and you're going to look at the simulation and try to answer them on your own. And then we will talk about the answers to some of these questions. Okay, and so first I want you to load the simulation, and I want you to take a look at the first set of questions. Okay, and so the first set of questions are these. Okay, so what is the difference between atoms and molecules? What do you notice about the atomic motion at a temperature of 0 K, or what we call 0 Kelvin, which is also called absolute zero? Um, and by the way, people are asking, like, how do you get to 0 Kelvin? There's a temperature switch on the simulation, and so if you just pull it down to cool, if you cool it down enough, you can eventually get the temperature to 0 Kelvin. Okay, so that's how you get to 0 Kelvin. Um, as we increase the temperature by a few degrees Kelvin, what changes specifically about the motion of the atoms? And then finally, as we continue to add more and more heat, what happens to the structure of the atoms? And so I want you to have these questions, and I want you to try to answer them now, um, and then we'll talk about them momentarily. Okay, so here we have the simulation, and I'm just going to take a look at, I guess we can look at argon, because why not? Um, and so the first question asks about the difference between atoms and molecules, and this doesn't really have to do with the simulation, but this is just going back to your prior knowledge from chemistry or from a past science class. Basically, the difference between an atom and a molecule is everything is made of atoms. All matter is made of atoms, and there's different types of atoms. In fact, there's a whole periodic table filled with different types of atoms. Now, sometimes atoms can be held together in groups, and those groups are what we call molecules. And so here, for example, we have individual argon atoms, but one example of a molecule would be like water. Okay, water is H2O. It's a molecule made of 3 atoms, right? 2 hydrogen atoms and one oxygen atom. And so every one water molecule actually is made of 3 atoms. So molecule is just like a group of atoms. Okay, so here we have water, oxygen, which is a diatomic, what's called a diatomic molecule, naturally exists as a molecule, meaning it's still oxygen, but it actually comes in twos. And so two oxygen atoms make up one oxygen molecule, if that makes sense. Okay, so that kind of addresses the first question. Now, the second question um, says, what do you notice about the atomic motion at a temperature of 0 Kelvin? So what we're going to do is we're going to look at the simulation. The temperature is shown up here, and we're going to cool it down until we get to 0 Kelvin. Okay, as we do that, notice what's happening to the motion of the atoms. Hopefully you notice that they're starting to slow down. They're vibrating, right? They're still kind of shaking a little bit at 1 Kelvin, but they slow down considerably. watch what happens when I keep going and I get to 0 Kelvin. Okay, so I'm at 0 Kelvin, and notice that the motion of the atoms, even that tiny little vibration, is stopped completely. And so 0 Kelvin is what is known as absolute zero. Okay, it is by definition the lowest possible temperature you could have in the universe. Okay, there is no temperature lower than 0 Kelvin. That's how it's defined. That's why it's called absolute zero. And that is the temperature at which all atomic motion in an object stops. All the atoms stop vibrating, all the molecules stop vibrating, etc. Now, in real life, you cannot actually get something down to absolute zero. Even space is not quite at 0 Kelvin, but it is really close. Um, and so this is kind of like a theoretical construct, but the concept of absolute zero is it's the lowest possible temperature any object could reach, because that's the temperature at which all atomic motion stops. Now, the next question says, as we increase the temperature by a few Kelvin, what changes about the motion of the atoms? And so we kind of saw this as we were cooling it down, but as I increase the temperature, the whole block of atoms just kind of shifted up a second ago. That doesn't really mean anything. That's just because of the simulation. But if you look at the motion of the individual atoms, they are vibrating, they're shaking. Okay, they're moving in place. And if I increase the temperature a little bit more, notice that they are vibrating faster, right? They're shaking a little bit faster. Right, and so that kind of goes to that third question, what changes about the motion of the atoms as you increase the temperature? The motion increases, okay, they're moving faster. And then the last one says, as we continue to add more and more heat, what happens to the structure of the atoms? And so what we have here right now is what's called a solid. Okay, and in a solid, the atoms are tightly grouped together, as we saw. But what can happen is as you increase the temperature of the solid, the atoms, even within the solid, are vibrating in place. And at some point, if they vibrate with too much energy, they actually have enough vibrational energy, which is actually kinetic energy because it's energy of motion. They actually have enough kinetic energy to start breaking the molecular bonds that they have. Okay, and so what happens then is you go from having a nice, neatly organized structure of atoms to this kind of lumpy mess. Now notice the atoms are still more or less connected, but they're kind of less organized. And so this is what we call a liquid. Okay, it's still, you still have the atoms, they're still like connectiveness, but it's way less organized than it was before. And so basically what you just saw in the simulation is melting, right? We took the argon atoms from a solid to a liquid. And as we continue to increase the temperature even more, they continue to shake faster and faster. And at some point, you can even see some individual atoms are starting to shake so much that they actually tear themselves apart from the group. And so if we continue to increase the temperature, at some point, all of the atoms start to break up. And now we get what is called a gas. Okay, and so, that's the difference between a solid, liquid, and gas at the atomic level. And you can't see it on the simulation, but there's actually a fourth state of matter called a plasma. And basically, a plasma is kind of like a super hot gas where the temperature is so hot that normally in an atom you have like, the nucleus in the center and you have the electrons on the outside. But in a plasma, the temperature is so high that you have a gas, but the temperature is so high the electrons themselves have come off of the atoms. And so rather than having, um, atoms with electrons, you basically just have a bunch of like electrons um, mixed in with the gas particles, and that's what a plasma is. If you've ever heard of plasma, some people call it like the fourth state of matter. All right, so hopefully you were able to somewhat successfully answer those questions. I do have another group of questions I want us to take a look at. See if you can, actually, let me go to the simulation. What I want you to do now is I want you to click at the bottom to where it says phase change. Okay, and when you get to this tab, there's a gauge showing you the pressure. Okay, there's a pump, so we can pump more atoms into the thing. Let me change it back to argon. And we can also change the size of the container by pushing on the container, as you can see. Okay, now notice the pressure gauge right now reads 0. Okay, ATM is atmosphere. atmosphere is a unit for pressure. And so basically what this is saying is there's no gas pressure inside the container. All right, so I want you to play around with the simulation, and I want you to see if you can answer these questions. Okay, so based off of your observations from playing around with the simulation on your own, I want you to hypothesize what you think temperature is a measure of. And of course, you can look this up in 2 seconds. I don't want you to do that, right? I care less about you getting the correct answer, and I want to know if you can, reason this out on your own. Okay, so based off of just what you see, what do you think temperature is a measure of? In other words, as the temperature goes up or down, think about what's changing with the motion of the atoms. What do you think temperature actually quantifies? The second question is, as you add more gas particles to the container, how does the pressure change? As you decrease the container volume, because remember you can push in the top of the container from the top, how does the pressure change and the temperature? And then this last one is really kind of hard to figure out just based off of observations. But based off of your observations, what do you think pressure is a measure of? And you could be completely wrong, and that's completely okay. I just want to see what takeaways you can get from playing around with the simulation. Okay, so based off of playing around with the simulation, what do you think pressure is a measure of? Okay, so pause there and try to answer that question. Okay, so the first one we kind of alluded to previously, but temperature obviously has something to do with the motion of the atoms. As we saw, as we increase the temperature, they start to vibrate faster. And so it turns out that it does have to do with the motion. And something we've talked about previously that has to do with motion is kinetic energy. And so the actual correct answer, which if you didn't say, I completely understand because I mean, how would you know? But I'm telling you the correct answer now. Um, Temperature is actually a number that measures the average kinetic energy of the atoms or molecules making up an object. And so that's why we see as we increase the temperature, right, we're actually increasing the average kinetic energy of the atoms, which is a fancy way of saying we are making them move faster, right? Because kinetic energy is energy of motion, and so increasing the average kinetic energy is basically increasing the amount of motion the atoms have. And so that kind of goes to the first answer. Now, the other ones have to do with pressure. So let's play around with adding more gas. Right now, the pressure gauge reads 0. If I take the pump and I pump in more gas particles, let's see how the pressure changes. Notice the pressure was 0 until a second ago. All of a sudden, it started going up mysteriously. Okay, and so I think it's probably a reasonable hypothesis to say, if you add more gas particles to the container, it's going to increase the pressure. Now, that doesn't tell us what pressure is necessarily, but I mean, it's pretty easy for us to draw that conclusion because you can see I'm still adding more gas particles and the pressure's still going up. Interesting. All right, so let's back up and take a look at that next to last question. As we decrease the container volume, how does the pressure change? What about the temperature? Okay, so notice as I decrease the container volume, nothing happens to the pressure. When we talk about pressure in this context, we're talking about the pressure of a gas. And so since this is a solid, you can tell from the structure, we don't have any pressure until it becomes a gas. Once we squish it enough, boop, you can see the pressure start to increase. Okay, not only that, but the temperature went up as well. Let's see that one more time. Pay attention to the temperature as I compress this gas. Okay, so here we can see the temperature went up and the pressure also went way up. Now, the temperature going up, remember, temperature is a measure of the average kinetic energy of the atoms. And so the temperature going up basically means that the atoms now have more kinetic energy than they had before. So, well, how did they get more kinetic energy? You can't just create energy out of nowhere. But basically what happened is the top of the container ran into all those atoms and transferred some of the energy through that collision. Kind of like how if you hit a tennis ball with a tennis racket, the the ball is going to gain energy. That's basically what just happened, except the top of the container is like the racket, and all of those atoms are basically like bajillions of little tennis balls getting energy when they get smacked. Right, so that's why the temperature went up. Now, what about this pressure? Well, we saw the pressure went up from 0. Okay, and so if we keep compressing it more, the pressure goes up more. So clearly, and if the pressure gets too high, the thing blows up. That's bad. So clearly, we know from the observations, pressure has kind of something to do with the number of gas particles we had, because as we added more gas, the pressure went up. It has something to do with volume, obviously, because when we decrease the volume, the pressure went up. Um, and we also can kind of see as we increase the temperature, once it becomes a gas, the pressure starts increasing. And as we increase the temperature more and more and more, the pressure also correspondingly increases. Okay, and so based off of those three observations, we got to think, can we figure out what is this pressure thing actually telling us? Like we know, okay, so temperature has to do with average kinetic energy. Fine. What about the pressure inside this container? Okay, and it's not so easy to figure out just by playing around with the simulation. And so I'll tell you the answer, or I'll show you the answer. So right now we have 0 pressure because we have a solid. Okay, solid argon. And now we have liquid argon. I want you to pay really, really close attention to that pressure gauge, because as I increase the temperature, what you're going to see is it's going to go from a liquid to a gas, and you're going to have individual atoms break off from the group and collide with the container wall. And so I want you to watch what happens when that happens. Okay, right there, notice it says 0.3. That's back to 0. Right there, something happened. Oh, and something happened again. Okay, now it's at 0.2. Now it's back to 0. Okay, so what is actually happening that's causing the pressure to go up? Well, if you look closely, you'll notice the pressure changed every time one of these atoms collided with the container walls. Okay, if we increase the temperature, we get more of those collisions. Okay, here's the answer to that last question. What is pressure a measure of? All right, well, pressure is actually a measure of the frequency of collisions that the gas particles make with the container walls. Okay, in other words, how often do those gas particles collide with the container walls? The more often they collide, the higher the pressure. Okay, that's why we didn't have any pressure with a solid, because there were no gas particles. That also explains why as we increase the temperature, as the atoms start to move faster, as they gain kinetic energy, of course they're going to hit the container walls more often. As we add more gas in, okay, obviously if there's more gas atoms, there's going to be more collisions. That's just common sense. And if we decrease the volume, we know if they're moving around in a smaller space, then of course they're going to collide with the walls more often. And just to be clear, we're talking about collisions not the atoms colliding with each other, but the atoms colliding with the walls of the container. Because every time there's a collision with the walls of the container, each atom puts a little force on the container, and we'll talk more about that later. Okay, so it's not the collisions between the atoms, it's the collisions between the atoms and the container, the walls of the container that they're in. Okay, so that is what pressure is a measure of. Okay, and so I want to give you a chance to just kind of write down some definitions. Okay, some of these we've already talked about, and some of them we'll talk about in the next video. Okay, we've kind of already talked about temperature and pressure. Internal energy, we haven't talked about heat, we haven't talked about thermal equilibrium and phase change. All of those are new terms. Okay, but in this unit, definitions are important, and so I want to make sure that you get the correct definitions written down in your notes. All right, so we're going to go ahead and stop this video here. Um, As always, please let me know if you have any questions, and I'll see you guys in the next video.